This brings us to standing sound waves. So if you have a tube that's open on both ends, then you get regions of compression and rarefaction. But when you have a standing wave, that region of compression alternates between compression and rarefaction very quickly, and the region of rarefaction alternates between rarefaction and compression very quickly, and that region in the middle, right, always stays around atmospheric pressure. That we would call a node. So right here in the middle of the tube, we would have a node. Now at the ends of the tubes, we're connected to atmosphere. So what's the pressure outside at the ends of the tube? Well, as we saw with water flowing through pipes and stuff, whenever you're hitting atmosphere, the pressure here must also always be atmospheric pressure, right? So here we have a node. So we have a node at the two endpoints, and in this case, we also have a node in the middle. This creates a standing sound wave. You can hear this, for example, with a toy that I found in our toy box. Super fun. I should accidentally break this. But yeah, so I can create a standing sound wave. It sounds like that through this tube that is actually open at one end. There you can see it's open there. And actually this one looks like it's closed at that end. It's got two little plastic pieces that come together where I can just barely put the air, through that little slit. So, however, we can fit several different modes inside of here. That was not the lowest mode I can make. So in this tube, I can create a... So I can get about 3 different notes out of this one. I found another one, super fun, awesome sounding. Yeah. This one I can make about 2 different notes. Well, why is that? The reason is only certain wavelengths can actually fit inside a tube of a given length. And by the way, in case you're curious, this has the same sort of open on one end, closed on the other type of device. Should throw those away. Okay, so let's take a tube that's open on both ends. Here we have a tube, right? Both endpoints are nodes, and right in the middle we have an antinode. This is the lowest mode, and I'm sorry for the difference between node and mode. This is the lowest mode possible. We call this mode number 1. Right in the center we have an antinode where oscillations between compression and rarefaction occur very quickly. And if I were to write down what the wavelength is, right? What's the wavelength of this wave in relation to the length of the tube? Well, we can see here we have half of a wavelength. So this is L/2, okay? If I go to the next highest mode, the next mode up, right, I'm required to have both ends be a node, and I can stick one more node in the middle, and now I see the wavelength here is equal to exactly the length of my tube. And I can continue this right to the next highest mode. Here I have one full wavelength plus another half, which means lambda 3 is equal to 2/3 of the length of L. So this is 2L/3. Now I can generalize this, right, in the form that's actually written right there. Lambda m, where m is the mode number, is equal to 2L over the mode number m. Okay, that's what we see right here. Now this is also true if I have a tube that is closed at both ends. Now it's kind of hard for us to imagine, but there are, some structures you would have to have like a small hole, right, for air to go in and out. But if the ends are both closed, then here we definitely have antinodes. You can think of the ends of the tube as being places where you can have high pressure or low pressure very easily. Then the lowest mode that can fit is with a single node in the center, 2 antinodes on either side. And this is also 1/2 a wavelength, right? 1/2 of a wavelength fits inside L. So the wavelength is equal to, oh, I'm sorry, that's supposed to be 2L. Whoops, let's change that. 2L. Hopefully you caught that earlier. Right, so the wavelength is twice as long as the tube. It doesn't all fit inside there. The next one up, again, we're required to have antinodes on the 2 ends. I put an antinode in the middle, and then 2 nodes fit in between them. And this is one full wavelength. So the wavelength 2 is equal to L. So an open tube and a closed tube are identical to a wave on a string, right? So we see here the wavelength is given. I can find the frequency, right? F1 is given by V over lambda, right? The speed of the wave divided by the wavelength. And if we work that out, what is that? That's V over 2L. V over 2L. Likewise, F2, the second mode frequency, is V over lambda 2, or simply V over L. And likewise down the line, and we see that our frequency, right, of a given mode is given by M times V over 2L. Or since V over 2L is the fundamental frequency, we can just say that this is M times the fundamental frequency, where M is just some whole number. Okay, so these are all very important. This is a good time to check out the Rubens tube videos. I posted a couple that I liked from YouTube. I'll put them in the playlist. And yeah, we were going to do that in class. We actually did that in the Monday, Wednesday section. I don't think we'll have time to do that next week. So I'm sorry, but the videos on YouTube are maybe a little more sophisticated than we were able to manage. So enjoy. And then the last kind of standing sound waves we can create in a tube are tubes that are open on one end and closed on the other. So this requires us to have a node, right, at the open end, because this is always going to be atmospheric pressure, right? I don't know if I said it specifically, but we are plotting atmospheric pressure as a function of the length of the tube, along the tube length. And then the other side is going to be an antinode because it's closed here. So mode 1, right, we see we can fit a quarter of a wavelength in here. Mode 3, we jump ahead, we can fit 3/4 of wavelength because we've gone from 1/4 to 3/4. 2/4, or in other words, a half a wavelength doesn't fit inside an open closed tube. It doesn't work that way. Half a wavelength would have either 2 nodes or 2 antinodes, and that doesn't fit in an open closed tube. So the mathematics are slightly different. I'm not going to focus on them quite as much as the other ones because the open, close, and waves on a string all have the same mathematical formulas. But standing sound waves, we see that the wavelength for mode M is given by 4 times the length of the tube divided by our mode number. The frequency, because it's V over lambda, is again M times V over now 4L, or just some mode number times our fundamental. But note, in this case, our mode numbers are always odd. Okay, and that's because of the situation of having one side open, one side closed, so not every single wavelength will fit inside these tubes. Some examples of open-closed tubes are reed instruments, like clarinets and oboes and things like that. Open tubes are more like flutes and horns. Trumpets, I believe, are open-closed because your lips press together like this to create a solid wall, if you will. So that's standing sound waves. Yeah, and I will go and do some more example problems on other videos.